as we will see, if what we had in the bottle was an ideal monatomic gas, then if we could determine the number of moles of gas, and we can easily do that using PV equals nRT, knowing our original pressure, volume, and temperature, we can easily determine how many moles of gas there are. We could use that information to determine how much thermal energy had to be added if the gas was monatomic. It isn't, and we'll consider what we have to do with a diatomic gas after we see what we do with a monatomic. Okay? The amount of thermal energy added at constant volume, this reads delta QV, and let me zoom in on that part of the page just a little bit. Okay, this delta QV, which is a delta Q that has to be added while the system is a constant volume, and remember this system is a constant volume while the water is rising in the tube and before it starts flowing out of the end of the tube, is going to be 3/2 R, where R is just your gas constant, 8.31 joules per mole Kelvin. N is the number of moles, and delta T is the temperature change. Okay? So at constant volume, this is the amount of thermal energy that you have to add. And remember, we could easily determine that if we had a monatomic gas. We could easily determine the number of moles. We've observed the temperature difference. What did we go from 297 to 330 Kelvin? Something like that. So we could determine the amount of thermal energy required. If the gas changes, if the thermal energy is added to gas at constant pressure, fixed number of moles, then the gas is going to expand, and in the process of expansion, the gas is going to do some work, because to expand it has to exert a force against air pressure, for example, if it's expanding at atmospheric pressure, or whatever pressure it's expanding at, it's going to have to exert a force against the pressure through a distance in order to expand. And in that case, we have to use the amount of thermal energy required is 5/2 R N delta T. This compared to the 3/2 R N delta T. You get an extra 2/2 of an R N delta T for expanding at constant pressure to do the work of the expansion. These relationships look a lot like specific heats. Okay, it's a lot like the specific heat where you multiply some constant times your mass times delta T. But now it's not a constant like 3/2 R times a mass delta T. It's a constant which is 3/2 R times the number of moles times delta T. We then call this 3/2 R the molar specific heat. It acts just like a specific heat when we're dealing with numbers of moles. And we call 5/2 R the molar specific heat at constant pressure. And we give those terms names. Well, symbols. It's very standard to use C sub V to stand for the molar specific heat at constant volume, and Cp to stand for the molar specific heat at constant pressure. The molar specific heat at constant volume, 3/2 R, turns out to be about 12.5 joules per mole Kelvin. At constant pressure, it turns out to be 20.3 joules per mole Kelvin, again for an ideal monatomic gas. Remember that what we have in our system is a diatomic gas, and we'll have to deal with that. The difference between the delta QP and delta QV again is the work done to expand the gas. Now this is the general scheme of how we're going to determine how much thermal energy goes into the system. Before we do that, we're going to want to identify the states of the system. And we want to identify these states very precisely and very specifically, and we'll see that in the next clip.